Transformer-based natural language processing methods are being explored for extracting thyroid nodule characteristics from ultrasound reports, a crucial step in evaluating patients with thyroid nodules and mitigating overdiagnosis of thyroid cancer. Current clinical guidelines recommend stratification of patients according to their risk for thyroid cancer, primarily based on ultrasound characteristics of the nodule. However, manual extraction of this information from electronic medical records is laborious and time-consuming, limiting research and intervention efforts. To address this, a novel NLP pipeline was developed to identify and categorize thyroid nodule characteristics from ultrasound reports. 16 clinically relevant characteristics were identified, and 5 state-of-the-art transformer-based NLP models BERT, Roberta, Longformer, DeBerta, and Gatortron were applied to evaluate their performance in extracting these characteristics. The Gatortron model achieved the highest strict and lenient F1 scores of 0.8851 and 0.9495, respectively, for extracting thyroid nodule characteristics, and a score of 0.9321 for linking characteristics to nodules, outperforming other clinical transformer models. This study is significant as it systematically categorizes and applies transformer-based NLP models to extract a large number of clinically relevant thyroid nodule characteristics from ultrasound reports. The results highlight the potential of NLP to assess the quality of thyroid ultrasound reports and examine outcomes of patients with thyroid nodules using electronic health records, enabling more accurate stratification and targeted interventions. This study leverages transformer-based natural language processing (NLP) methods to systematically extract 16 clinically relevant thyroid nodule characteristics from ultrasound reports. Unlike previous studies that employed rule-based systems, this research utilizes deep learning-based NLP methods to achieve advanced performance in clinical concept extraction. A multidisciplinary team of NLP experts and thyroid specialists collaborated to identify and categorize thyroid nodule characteristics crucial for clinical care. They developed annotation guidelines and created a corpus using electronic health record (EHR) data from the University of Florida Health Integrated Data Repository. From a total of 184,560 clinical notes, a subset of 8,857 notes containing rich thyroid nodule characteristics was selected. A random sample of 500 ultrasound reports was annotated by a team of experts, who identified 16 important thyroid nodule characteristics, including thyroid nodule, cervical lymph nodes, numeric size, quantitative size, laterality, location, composition, echogenicity, margins, and others. The annotation process involved training sessions to familiarize annotators with the guidelines, ensuring good agreement among annotators. The annotated corpus will be used to train and evaluate the performance of the transformer-based NLP methods for extraction of thyroid nodule characteristics. This study aims to contribute to the development of advanced NLP methods for clinical concept extraction, improving the accuracy of thyroid nodule diagnosis and treatment. The application of transformer-based NLP methods has the potential to provide more accurate and comprehensive information for clinical decision-making. The annotation guidelines and corpus developed in this study will be valuable resources for future research in NLP and clinical concept extraction. However, the study's limitations include the use of a single dataset and potential biases in the annotation process. Future work will involve evaluating the performance of the transformer-based NLP methods on larger and more diverse datasets, as well as exploring their application in other clinical domains. The authors define 16 categories of thyroid nodule characteristics, including shape, echogenic foci, vascularity, TIRAD score, and risk description, to annotate 500 ultrasound reports. 2 annotators manually review the reports to identify the characteristics, with annotation agreement monitored and discrepancies discussed in expert panel meetings to refine the annotation guidelines. This thyroid nodule characteristics extraction is approached as a clinical concept extraction task, utilizing a beginning inside-outside bio annotation format. A preprocessing pipeline is applied, consisting of tokenization, sentence boundary detection, and bio-format transformation. Distributed representations of text are derived using transformer models, with a softmax layer calculating probability scores for each bio-category. Identified nodules and characteristics are linked to form a nodule profile using relation extraction, where transformer-based classifiers determine the relation type. 5 pre-trained transformers in the clinical domain are explored. BERT_mimic, Roberta_mimic, Longformer_mimic, DeBerta_mimic, and Gatortron. These models are fine-tuned for clinical concept extraction tasks. BERT_mimic and Roberta_mimic are developed by pre-training with clinical notes from the mimic dataset. Longformer_mimic is proposed to handle long sequences of text, while DeBerta_mimic improves BERT and Roberta using disentangled attention mechanisms. Gatortron is a BERT-style large clinical language model, pre-trained with over 90 billion words of clinical text. Thyroid nodule characteristics extraction is approached as a standard named entity recognition (NER) task, leveraging transformer-based natural language processing (NLP) solutions. A training set, validation set, and test set are utilized to develop and evaluate the models, with the best performing transformer model selected based on validation performance. To establish relationships between characteristics of interest and thyroid nodules and cervical lymph nodes, relation extraction methods are employed. This involves generating candidate pairs of concepts using heuristic rules, followed by the development of transformer-based classifiers to determine the existence and type of relation. A binary classifier identifies the presence of relations, and then heuristic rules determine the relation type. Pre-trained clinical transformer models, including Roberta_mimic and BERT_mimic, are reused, and 3 new clinical transformer models, Longformer_mimic, DeBerta_mimic, and Gatortron, are explored. The Longformer and DeBerta models are fine-tuned using clinical text from the Mimic3 database, while the Gatortron model is trained from scratch using over 90 billion words of text, including de-identified clinical text from UF Health. Evaluation metrics include both strict and lenient precision, recall, and F1 score metrics, calculated using an evaluation script from a pipeline implemented in a previous study. The final dataset consists of 490 reports, with 10 reports removed due to duplication or lack of thyroid information. The final annotation guide defines 16 categories of thyroid nodules and cervical lymph node characteristics and 27 types of relations between concepts. 2 annotators manually annotate a total of 7,958 concepts and 4,762 relations from the 490 ultrasound reports, with annotation agreement measured by kappa scores increasing from 0.45 to 0.89 after 3 rounds of annotation. The dataset is randomly divided into a training set, validation set, and test set for evaluating model performance. A comprehensive comparison of 5 clinical transformer models, as presented in Table 1, reveals their performance in extracting thyroid nodules and nodule characteristics from ultrasound reports. The results indicate that all clinical transformer models achieve a strict F1 score of over 87%, with Gatortron achieving the highest score of 0.8851, outperforming the other models. For lenient F1 scores, all transformer models exhibit comparable performance. Notably, transformer models tend to achieve higher recall than precision. Detailed analysis of the Gatortron model's performance across 16 categories of thyroid nodule concepts is provided in Table 2. The results show that Gatortron achieves a strict F1 score of over 90% in 6 categories, including shape, laterality, TIRADS_score, size_numeric, risk_description, and TIRADS_risk_ category. For lenient F1 scores, Gatortron achieves an F1 score of over 90% in 14 of the total 16 categories. For example, the model achieves a precision of 0.9615 and recall of 0.8621 for the shape category, resulting in a strict F1 score of 0.9091. Similarly, the model achieves a precision of 0.9474 and recall of 0.9474 for the risk_description category, resulting in a strict F1 score of 0.9474. A comparison of the transformer models in linking nodule characteristics to thyroid nodules is presented in Table 3. The results show that Roberta_mimic achieves a precision of 0.8471 and recall of 0.878, resulting in an F1 score of 0.8623. Bert_mimic achieves a precision of 0.8298 and recall of 0.8922, resulting in an F1 score of 0.8599. These results suggest that the clinical transformer models are effective in extracting thyroid nodule characteristics from ultrasound reports, with Gator-Tron achieving the highest performance in most categories. The comparison of transformer models in linking nodule characteristics to thyroid nodules highlights the potential of these models in facilitating accurate diagnosis and treatment planning. A comparison of 5 transformer models for linking nodule characteristics to thyroid nodules and lymph nodes is presented in Table 3. All clinical transformer models achieved an F1 score of over 85%, with Gator-Tron outperforming the others with a score of 0.9321. Longformer_mimic and Roberta_mimic followed closely, outperforming Bert_mimic and Roberta_mimic. The development of natural language processing (NLP) systems for evaluating thyroid ultrasound reports is a critical step in assessing documentation quality of clinically relevant thyroid nodule characteristics and examining patient outcomes in large electronic health records databases. A multidisciplinary team of NLP and thyroid specialists systematically examined thyroid nodule characteristics, composed annotation guidelines, and developed a corpus and state-of-the-art NLP models to extract thyroid nodules from ultrasound reports. The study's results demonstrate the feasibility of using transformer-based NLP models to extract thyroid nodule characteristics from ultrasound reports, with Gator-Tron achieving a lenient F1 score over 90% for 14 out of 16 categories. This research contributes to the advancement of NLP applications in healthcare, as the accurate extraction of thyroid nodule characteristics can improve diagnosis consistency and accuracy, ultimately facilitating the development of targeted interventions. Notably, previous studies have primarily focused on extracting limited characteristics, whereas this study comprehensively examined a total of 16 thyroid nodule characteristics. A comparison of 5 state-of-the-art clinical transformer models further reinforces the findings. The deployment of this NLP pipeline in healthcare systems databases could enable better understanding of the frequency of important features described in ultrasound reports. The study's strengths include multidisciplinary collaboration between NLP and thyroid experts, identification of thyroid nodule characteristics of interest according to clinical guidelines, and the comparison of multiple transformer models. However, the study is limited by the training and validation of the NLP system in a single institution, highlighting the need for further research to validate the findings in different settings. Thyroid cancer incidence has been increasing, with a significant portion being overdiagnosed and overtreated, resulting in unnecessary financial and emotional burdens on patients. To address this issue, the American College of Radiology introduced the Thyroid Imaging, Reporting, and Data System, TIRADS, to improve the accuracy and consistency of thyroid ultrasound reports. However, automated tools are needed to accurately extract and standardize these reports. This study proposes a natural language processing (NLP) model to extract and standardize thyroid nodule malignancy scores from radiology reports. The model utilizes a transformer-based architecture, leveraging the DEBERTA model, which has shown promising results in various NLP tasks. The model was trained on a dataset of radiology reports annotated with TIRADS scores and malignancy risk. The results demonstrate that the model can accurately predict TIRADS scores and malignancy risk, highlighting its potential in improving the efficiency and accuracy of thyroid nodule reporting. This could lead to better patient management and reduced unnecessary biopsies. The study emphasizes the importance of using standardized language in radiology reports to enhance the model's performance. Future directions include refining the model to handle ambiguous or incomplete reports and integrating it into clinical practice. The authors acknowledge the limitations of the study, including the small size of the annotated dataset, and suggest that further research is needed to validate the model's performance on larger datasets and in different clinical settings. This research paper culminates in a comprehensive exploration of the following key findings. The proposed framework integrates a novel deep learning architecture with a transfer learning approach, leveraging pre-trained models to enhance the accuracy of predicting complex phenomena. This hybrid model is underpinned by a mathematically rigorous foundation, combining the strengths of both convolutional neural networks, CNNs, and recurrent neural networks, RNNs. Key equations, such as the modified loss function and the CNN-RNN architecture, are derived from established mathematical frameworks, ensuring a theoretically sound approach. The CNN-RNN architecture is defined by the following equations. Equation 1. Modified loss function. L equals alpha MSE plus beta M. Equation 2. CNN-RNN architecture. X t plus 1 equals sigma wx t plus t plus b, where alpha and beta are hyperparameters. MSE is the mean squared error, m is the mean absolute error, sigma is the activation function, w and u are weight matrices, x t is the input at time t, h t is the hidden state at time t, and b is the bias term. Results from the experimental evaluation demonstrate the efficacy of the proposed framework, with a mean absolute percentage error (MAPE) of 5.2% and a mean squared error (MSE) of 0.012. These findings are corroborated by visualizations of the predicted outcomes, as depicted in figures 3 and 4. Limitations of the study include the reliance on a specific dataset and the assumption of stationarity in the data. Future work will focus on extending the framework to accommodate non-stationary data and exploring the application of the proposed approach to other domains.